Now, just because a token follows the ERC20 token interface and it defines the functions the way that you would expect, doesn't necessarily mean that the token actually behaves the way you would expect. So there are a bunch of different examples of this. In a later video, we'll go over some examples of security failures that often involve ERC20 tokens. I just want to point out a couple of examples for now. So here's one example of a token. This is called the useless Ethereum token. It was always meant as a joke, although it actually raised a bunch of money during an ICO anyway, despite if you go to the website, it'll be quite clear that this isn't actually promising anything. It's kind of a parody of a smart contract. But nonetheless, it actually does have a token page. You'll notice if you go to this token page that it warns you that something's wrong with this. But leave that as a puzzle. You can go and look at the code associated with it. So here's the useless Ethereum token in all of its glory. You can see it's pretty similar to the test token that we created. Like, it has a mapping of balances like you'd expect. Similar kind of structure like any ERC20 with the name and symbols. But there's something really badly wrong with this smart contract. See if you can read through the definition of the different transfer methods and transfer from methods, and see if you can figure out for yourself what the problem is. Otherwise, you can follow the link on these slides or even the warning on the Etherscan page for the useless Ethereum token to see what the hazard was that made this actually quite vulnerable and make it possible for people to steal all of the tokens out of it. Now, let me go into a little more detail on a particular bug that's sort of interesting that occurred with a website dealing with ERC20 tokens. So let's just dig into a little more detail into what a transfer method looks like. So as we mentioned earlier, when you make a function call to an Ethereum contract, all of the data, including the function, the name of the function that you're trying to call, and all of the arguments that get passed are actually packed into a single long blob of input. And when you look at this through a website like Etherscan, it breaks out the different components of this. So for example, a call to the transfer method, it would identify, okay, the first 4 bytes of this input correspond to the tag, the name of the function that you're calling basically, and the next 2 arguments, the next 2 32-byte chunks correspond to each of the 2 arguments to the function. So here's what happened. There was a website that would hold tokens on your behalf, keep track of your account, maybe your email address as their way of having an account for you, and at a later time, if you wanted to withdraw coins to an address of your choice, it would allow you to do so. Now, what would happen is that this website, because it would allow you to enter in the address you wanted to withdraw the tokens to, and it would then assemble a transaction, a withdrawal transaction to, or a transfer transaction rather, to actually transmit those tokens to you when you wanted to take them. Now, because each of the arguments has to be packed into 32-byte values each, but addresses are only 20 bytes. What this website did is it would take 12 bytes of padding, add it to the 20-byte address in order to form the 32-byte word corresponding to the first argument to transfer, and then the amount that you wanted to have transferred to you as 32 bytes for the second argument. Now, the problem was the website didn't actually check that the address you tried to initiate a transfer to was actually the full 20 bytes. So what could happen is you could paste in a 17-byte address instead. And what happened is the way that the website would do the combining of the arguments into this function, what would happen is that it would end up having the total remaining number of bytes be padded towards the end. You would end up with 3 extra bytes of padding at the end and 3 0 bytes of padding in like the least significant bits of the address filling it up. So what's the problem of this? Well, by adding these extra zeros to the least significant bits of the amount, the website would be thinking you were only withdrawing 55 in hex values. That's how much it would check you had in your account. But when it actually created the transaction had the effect of creating a transfer for thousands of times that. In this case, 3 hex digits of 0 more times transferred to you than the website intended, or than the website thinks you had in your account balance. Now, in order to actually exploit this, you would have to do something a little bit clever, which is that you would actually have to come up with an address for which you know the private key, but that the last few digits of the address were all 0. So that when the malformed address with 0 digits added on top of what you actually put in the text field was created, that would end up as a 20-byte address for which you know the corresponding secret key. This exploit would basically allow someone to take, even if they had a really small amount of balance on this website, they'd be able to withdraw the entire balance of tokens that this website had on behalf of any of their users. I think the end of this story is that this exploit was disclosed and ultimately patched before anyone took advantage of it to rip off this exchange website. Okay, here's one more interesting story involving ERC20 token contracts. A Reddit user noticed that some ERC20 token contracts are actually owners of their own tokens, which is a little bit strange, and it turns out when that happens that it usually means that the tokens are actually stuck inside a contract. Now what this means is you can actually go and see this. So just for example, here's the Gnosis ERC20 token contract. And if you take the address of the contract itself and go to the Read Contract tab, look for the balance of method, paste that address in there, you'll see that this contract actually has some balance of its own tokens. Now, what happened is this results when someone has accidentally entered in the address of this contract in the to argument of the transfer method, not just the contract that the method is being invoked on. It essentially transfers their tokens to the contract itself as though the contract were going to become the owner of those tokens. However, when this happens, the contracts are stuck because the only way that those contracts could be moved is if this contract had some way of invoking a transfer on itself. And when reading the code for most of these contracts, they don't have any ability to make a transfer, to initiate a transfer from itself as an owner. So effectively, this contract has some balance of these tokens, but they're as good as lost. It's like transferring tokens to an address of someone who has lost the private key. Somewhat related and sort of interestingly, you'll find that there's lots of contracts that aren't just holders of their own tokens, but are in fact holders of tokens from other contracts. One of the reasons that this has happened is from airdrops. That's when a token, when it launches, it gives away portions of its token balance to basically other people with addresses that are known on the Ethereum blockchain. Many of those are other contracts, including ERC20 token contracts, but for the most part, contracts, unless they were explicitly written to do this, they don't have any ability to initiate transfer methods on other ERC20 token contracts to move them. So for the most part, when a token turns out to be a holder of an other contract's tokens, those tokens are effectively stuck. You could write the contract so that it would be able to generate such transfer methods. You would have to have code in here that would initiate a transfer call on another contract to do so, but that's not terribly common. So that's just a little curiosity, something unusual you would find if you look at which addresses on the Ethereum blockchain have balances of which other tokens.